better? Hello? Okay, great. This is better. So, as I said, I work for GoPro, and so GoPro, as you know, is famous for action cameras, but also we have a great software teams. So working from cloud, of course, the data science engineering infrastructures and data analytics, as well as the other media services and the cloud subscription services. And so we have a great software engineering team. So we always support community effort like this to try to help to make sure the community sharing knowledges and sharing experiences. So tonight we have 3 great talks. The title is "The Skill at the Lyft and Uber." So the first talk is coming from the Lyft. They're talking about how to use Spark in Kubernetes clusters. So the speaker is Lee. He has been working with several companies before, and currently in the infrastructure team at the Lyft. And this talk he has presented previously at the Spark Summit. So welcome, Lee.
Can anyone hear me? Cool. Yeah, my name is Lee. So before I go to the slides after the slide, how many of you attended my previous talks at either Strata or Spark Summit? All right, okay, so hopefully you don't feel boring. The majority of the slides are the same, just a couple of slides changed. So content is similar, but we made some progress since then. So right now I'm working at the data platform team at Lyft and leading quite a few different initiatives in the data infrastructure within the data platform. And the Spark on Kubernetes, this project is one of the projects I jump-started. I'm currently, previously also had different leadership roles at Salesforce, maybe, and a few other companies. So basically, this talk will divide into 4 sections. Most interesting part probably is the server, but we'll start with the introduction of the data landscape of Lyft. So this is what we have currently. It's still evolving, so this picture may change month to month. So at very high level, we have this different paradigm of data processing, data compute. There's a batch ingestion of ETL, mostly is the largest for your data cost is there. And the data streaming is another cost center, obviously. And machine learning platform, another one. To support machine learning platform for a user, so there's notebooks and BI tools. Sometimes they're interchangeable, surprisingly. And we do have query and visualization tools and quite a few in-house operational analytics tools, and some of them open source. Data discovery lineage we open sourced this year, which is called Analysts, which is very powerful data lineage and discovery tool. We also have our in-house machine learning workflow orchestration, and obviously running a few cloud platforms. Data infrastructure sitting at the core of our of the engineering side and product side of Lyft. We have internal, external data product services. That's critical services product depending on the data infrastructure to function 24/7. And internally, we also have the data portals for users, for business analysts, scientists, machine learning engineers to discover data, to discover data sets, discover the lineage of data set and where it's coming from, who is using it. On top of that, on the data portal, we have the workflow orchestration engine and SRI, SRO, SRA dashboards, and cloud infrastructure services as well, which is also we depend on. Since this talk will focus on Spark on Kubernetes, to set a context, Spark on Kubernetes fall into a large context of the batch compute at Lyft. We don't use Spark for streaming. Majority of our Spark workloads is batch compute and micro batch compute and machine learning compute. But this gives an example of one of the, we call most of the ETL batch compute. So those Lyft is an event-driven company, so we have all kinds of events coming from different systems. The internal, external systems, the relation database, p-value stores, document stores, system events coming from our infrastructures and services. All of them go through our ingestion pipeline and landing on two places. We have S3 as our backbone of majority of our data at rest, and then we run many different batch compute and transform and serve data to three categories of use cases. Analysts mostly providing services and product for our business and engineers internally building our tool services as well, and scientists that building some cool experimentation. Another landing pipeline goes through is Druid, which is serving our real-time needs for many of our real-time insights. This is another example of most of our design is evolving. We never stay still for even this one. I think it's outdated, but it's close. So at the very beginning, we have Hadoop and Hive about 2 years ago, and we started introducing Spark last year, and introduced Kubernetes also last year, and beginning to beta and pre-production last month in May, and we'll continue to scale the cluster to our intended ideal state. So we still have some work to do. We will talk about that in the later slides. This is our initial batch compute, mostly on the Spark and the Hive side. On the most of the jobs, we have. This is back in the beginning of 2018, a little bit over a year ago. We have a vector-based provisioning and control plane, and most of workflows running, including machine learning workflows, running through Apache Airflow to drive all our workloads on this many provisioned Hadoop clusters. At the time, we start building the data discovery and lineage to track the usage on that. So, yeah, before I turn to Kubernetes, try to set the stage what kind of challenges we're facing at the beginning of 2018. So first of all, like I showed in the earlier slide, we do have a vendor-based control plane, which is severe limiting our innovation speed. And we do also have limitation of most of our ETL at the beginning of 2018. So we have Spark. Most of Spark is machine learning only. They don't support ETL workloads. We call hybrid workloads. And many of the ETLs started in Hive, but they evolve into a state that is extremely complex to compute everything in SQL, especially using some fancy machine learning models within the ETL. And on top of that, we have many different teams moving at different speed with different requirements, and some of the teams that we have acquired over the years, they're using different environments. So we have those different dependencies and versions required or to be able to support on our platform in a resource efficient way. This is just an example. One of the SQL extracted from some of our ETL is some fancy SQL, which is not that great. Okay, someone's taking a picture of it. So, okay, hope everyone is familiar with Spark. So the reason we have we set our own simplified, unified solution is let's use Spark for not 100%, but let's say 99% of our ETL workload. The reason for that is multi-paradigm. We support Python, Java, all those different APIs, and we can talk to quite a different data sources. Also, Lyft, the batch data compute start as S3 and S3 at the beginning, but it won't stay that way. So with Spark, we have the flexibility to talk to many different data sources and data sinks. And when we start this journey, we are right on time when Spark 2.3 released with alpha or experimental support for Kubernetes. So we start looking into that interesting domain. So before you introduce Kubernetes, so what are the issues even with Spark on Hadoop? We have, like I said, mentioned, since we have multi-tenant environment, that we have many customers, different teams, different organizations that are building their pipelines in many different and diverse ways. They have dependencies, Python 2 and 3. Unfortunately, we have both Python 2 and 3. They have different Spark versions from 2.2 all the way to 2.4. And we already have many large share clusters. We are still growing, so we need cost efficiency for the clusters to be able to share workload. And on top of that, we have mixed requirement from both machine learning and ETL. Okay, what Kubernetes can help? Kubernetes is in its core, it provides layers of abstraction on top of the we call containers. It has, first of all, it has very vibrant. The CNCF foundation, cloud native compute foundation is a critical decision point for us to decide to choose Kubernetes. It's a very large community. And on top of that, there is a few points like very nice abstraction. The resource is always declarative. It's based on the principle of immutability infrastructure. And on top of that, there are abstractions called operators, CRDs, and controllers. So it's a very nice way. And on top of that, when you have the different data sources sitting on the data on Kubernetes, there is always availability of the service mesh, which can make the data available faster without transformation. So this is the CNCF landscape. This is what screenshot I took at the Spark Summit. I haven't updated. I think this one is even bigger. There's a lot of vendors, active vendors, and community contributors in the CNCF landscape. There's many pieces we choose from. So hopefully at some point when we finish this project, we can contribute some of our enhancement, internal enhancement to Kubernetes also back to the community. Some of our team members are working on those. So we have Spark from the open source Spark 2.4, 4.2.3, and we have Kubernetes. So what's still missing? Yeah, Spark on Kubernetes still in early days. If you take a look at the Spark documentation, it says this is experimental feature. Do not use it in production. So the big warning there. And scaling, single cluster. This is Kubernetes limit. Kubernetes in practice, when we launch this batch data, it is especially the large data compute. The single cluster, which is they have a single pane of failure, mostly on the control plane of the single cluster side. I mentioned CRD, the custom resource definition, which is abstraction in Kubernetes, so you can build layers of abstraction. Unfortunately, the abstraction layer with the corresponding controller, which is called operator, also have choking points, but you have a lot of CRDs. On top of that, the control plane, all this Kubernetes control plane or the CRD control plane in the abstraction you build, when you have to roll out different upgrades, patches, there's always a pain point, something will fail. And if you're lucky, if you're running on a public cloud, then that point will apply to you, the pod churn and IP allocation. When you have a lot of pods, in Kubernetes pod is a group of containers always launched together. The posture and IP allocation, you guarantee to be throttled, which will not be fun for you to run on public cloud. On top of that, on a single Kubernetes cluster, there's also issues with the default Kubernetes scheduler. When there's a lot of pods, requests coming in rapid fashion. On top of that, if you're using Docker registry on AWS, which is ECR, it can also fail. So, this is not updated, but should be okay. We have less than 100 petabytes of data lake on S3. We have less than 1 million, hundreds of thousands of batch jobs running on databases, thousands of EC2 machines, many different clusters and ACs. Not just EC2, but some other cloud vendor as well. So workflows, thousands of workflows running. Those workflows are driving most of the batch jobs, not all of them. Some of the workflows are also driven by our internal workflow orchestrator. So, how do we tackle this problem? If you look at, there's many different factors you can tackle. Highlight a few of those we call factors. Not all the factors are independent from each other, but there are some of the factors you can consider. The highlighted in pink one is the one I will talk more in the following slides. Some of the gray area is you can research by your own, but mostly it's building construct in Kubernetes, except the IP allocation rate limit. We're still actively working on our network infrastructure team to help us to optimize our IP space allocation strategy. So this is a similar architecture, similar as the original one, slightly changed. It's very abstract. There's not a lot of detail, hopefully. Well, on the Airflow side, we have a dual play of two different orchestrators, ETL workflow orchestrators through Apache Airflow, and our machine learning machine learning model ML lifecycle platform, which is a workflow orchestrator. Both of them are driving through our gateway and talk to our Kubernetes clusters. So we have similar construct as our Hadoop world, which then handful, or maybe a little bit more than a handful of clusters. And we have on our control plane, we build our two critical components. One is gateway. You can think about a router and it's a traffic router, or in the AWS sense, you can think about like AWS API gateway. In the service world, microservice world, but in the data world, it's similar. We call data gateway. And on the another critical component in the control plane is cluster controllers. You can think of this one as a coordinator across many different clusters to decide which cluster should join which construct and to run your job. Yeah, we still have the data discovery and data lineage, and on the control plane we do have our separate storage. Mostly it's a mix of RDS and S3. So, in order to have this flexibility of these different hierarchies, we introduced a few additional constructs on top of the Kubernetes building construct. The boxes in gray, building Kubernetes construct, you have the cluster, you have namespace, you have CRD, custom resource definition. In Spark case, it's Spark CRD, and you have Kubernetes Spark. But as we start scaling more and more systems, more workload, we notice that we need to introduce layers of abstraction on top of the existing Kubernetes construct. So we introduce 1, 2, 3 abstracts. So resource labels, which is a loosely coupled logical grouping of your compute resource, we call cluster pools, which is a pool of clusters serving a type of workload. But inside an individual cluster, we introduced a construct which is called namespace group, which have a group of Kubernetes namespaces, which can share similar provisioning and the security context, and then your Spark job will launch within in the Kubernetes namespace to a pod. There are a few schedulers in this hierarchy. I highlighted a couple of them. The cluster controller, the job I mentioned earlier in the earlier slide, job scheduler, I will talk more. In the later slide, namespace group controller, which I will talk more. The pod scheduler, I will talk about this in a new slide. I added since the Spark Summit talk. So multi-cluster. The reason we have multi-cluster is mostly is for separation of concern. This is an example. Security, they always run their own pool of clusters, so no one can touch. They also don't share the actual persistence. But majority of our workload, they share set of persistent buckets so they can talk to you. But it's all controlled through, if running AWS, it's all controlled through IAM role, which I'll talk about more, where the namespace group comes in. Each individual cluster is also have ASC auto-scaling group attached. So when there's a workload burst, it will auto-scale to a certain degree. Keep in mind, most of cluster, since the clusters, we have a heterogeneous workload, we have GPU workload, CPU workload. Even if you are building a single cluster with auto-scaling group, you are bound to have multiple auto-scaling groups. Some maybe for GPU workload, some for CPU workload. HA. So cluster pool, one of the advantages we have in the cluster pool is HA. I think that's obvious. Since I mentioned there's always downtime when you do cluster rotation and control plane update. We don't want to bring down this pool of workloads while we are doing those updates. So it's a nice construct for us to have the cluster pool in this case. Namespace. So namespace group. So why do we need namespace group? First of all, Kubernetes namespace is tiny. So if you have done any large concurrent workload on Kubernetes in a batch world, not in a microservice world, you probably can sustain around 3K per namespace. But in the batch world, when you have posture, this is the best we can get before your API, the Kubernetes API server, your SAP server will choke. So what we do, we introduce namespace group. We observed to a certain degree, namespace can improve the total number of active pods you can launch. When we introduce namespace group with everything in a capable cluster, you can launch, let's say, a little bit over 100, not 100, a little bit over 10K of active pods on a single cluster. And also it gives us a secure isolation through different IAM role binding. Another construct we have is pod sharing. So what do we do with pod sharing? Like I said, one of the major challenges we have when we're running all this Kubernetes workload, batch workload on the public cloud is the posture and the IP address issue is always a challenge. To give you a background on Kubernetes, one of the Kubernetes mandate is every pod needs to have an IP address, which is in a flat IP address, which is flat within the same flat IP address as your actual host load. So as you build more and more pods, you will quickly exhaust your IP address. If you imagine you have a VPC in AWS and its CR is /16, you only have 65,000 possible IP address before you burn down your VPC. So that's an interesting one. So pod sharing is one strategy we have. There's a limit issue, but we find out for certain workloads, if they're compatible, we share through a long-running Spark session with set of Spark drivers, a set of Spark executors. we don't churn this pod. This one is all done through this job controller. So certain workloads, if we decide the job controller decides they are not compatible, we do launch this individual dedicated pods. Another way we try to reduce pod chart is separation of certain aspect of our command, especially for SQL work. We still have tons of Spark SQL running as SQL, and there are tons of DDL commands sending through many of our different services, product and users, and machine learning notebooks. So we find out many of the DDL commands we can actually do pod sharing. So what do we do to separate? So for DDL commands, we do launch a fleet of Spark strip service. Keep in mind this strip server, we modify a little bit. We find out the open source 2.4.3 version of the Spark strip server is not entirely working well when you put auto scaling on there on Kubernetes, so we have to fork a little bit, not much, to make it work while we are sending this whole burst of DDL commands to the STS. For the rest of them, we go through the regular pod launch process. Another concept we worked on and we recently stopped working on, which is we find out Kubernetes is not taking care of this one the way we expected, which is called pod priority and preemption logic. Although Kubernetes 1.14, which is the newer version of the Kubernetes, latest version of the Kubernetes release, they fixed some of the issues, but the preemption is not always working when you have a large number of pods. So this one is actually working for us, taint and tolerations. So consider this is a construct that basically separate your physical load with different EC2 loads based on certain labels or taints, depending on what way you're looking at it. And we separate these different workloads based on these taints. There are certain workloads, for example, all our controllers, watchers we'll talk about later. Those control plane, they have dedicated EC2 loads, so they won't interfere between our control plane or the controllers and our data plane or the Spark jobs. And within the cluster of Spark jobs, we also have this different isolation, especially between GPU workload and CPU workload. This is another one. I borrowed a few the diagram based on this link. But idea is when we have this limitation of either from the Kubernetes side or from the upstream Spark side, there are certain things are missing. What do you do? So we dive into detail of how pod is launched on Kubernetes in a very, very detail. So this is a detailed diagram. You can take a screenshot if you like. So when a pod comes into a Kubernetes API, it goes through a pipeline of decisions and transformations before it's actually launched on a single load. We dive into a very detailed different pieces of the Kubernetes control plane to understand what we can do to optimize our pod launch process. So we mostly focusing on the mutating admission webhooks, which is part of the construct that Kubernetes provides in the Kubernetes internals. What we do there, we inject sidecars. We'll talk about more about the sidecars, but basically in high level, sidecar give us flexibility of logging. We can extract many different logs in different ways, send to different places. Metrics. We actually do on the spot transform of some of the metrics before we send over, and the proactive controller communication to our higher level abstract controllers to take action before something happens, and configuration. Also Spark 3, if you can wait, Spark 3 has this concept of pod template, so which can help some of the configuration changes. But as of Spark 2.4, many of the extensive Kubernetes configurations are not available to Spark Summit or to any Spark command. So we have to modify all those pod requests, which has very simplistic pod specification and attach a whole bunch of other configuration before we actually launch to, before we actually persist into etcd. This is part of the Kubernetes internal the pod lifecycle or logic. Once a pod is persisted on etcd, obviously there's a pod scheduler which do some magic. I will show you the magic later. Binding to a given node, and when the binding happens, then the kubelet will actually start launching your pod. Okay, pod scheduler. This is one thing we're actively working on. On the left side, this is the default Kubernetes scheduler. What this one is doing is it's very simple. In any vanilla version of Kubernetes, you have the scheduler binding your pod to a node, which takes a predicate, which you say which kind of node you want. This is like load selector and all those things, and goes through some priority and round robin to pick a node. But that's too simple. We find out in our cases, we need to customize, especially for certain workload. Instead of binding one by one by pod, we actually use like a GAN scheduler type of binding, where this placement engine happens. So we do have policies in place for certain workload. If you define a policy, we'll tell the placement engine either you place all our workload at the same time, and when all is done, then you call it done, or you don't place any of our workload on this cluster. This is especially important for this machine learning workload. So let's move on to the ECR. This is still evolving, but one construct we introduced which helps a lot, still not completely eliminate the issue of the ECR issue. We call Docker in Docker. What this one does is it pre-pull and pre-populate the Docker images on the individual nodes before you launch your containers. This is another component introduced, which is key critical to our scale. This, at high level, this is called config composer. Basically, this takes your Spark Summit, because we want to make our end goal of this project. We want to make the Spark as user-friendly as possible. So it's like a serverless API. People just can launch Spark job with a very simple click of command. So you can imagine most of the default won't work in that case. So what we do, we have this transformer on the configuration. So we transform all the defaults based on many different criteria, and the cluster status, namespace status, and the Kubernetes scheduler status is even watchers. And we transform your configuration through many layers of override before we send over to Spark operator to execute. Okay, this is another angle of viewing the controller. We used to have the REST endpoint. We recently replaced with gRPC to increase our throughput. And most of the watchers controllers interact with Kubernetes API. Kubernetes API has a very nice event watcher interface, control-based storage, and then across clusters we use Kafka, our dedicated control bus to interface with our cluster controller. There are some example of controllers. Job scheduler mentioned, config composer mentioned, namespace, pod scheduler, service controller, mostly is STS and Jupyter. Watchers for Kubernetes, for Spark. Spark operators, this is the Google GCP open source Spark operator right now is in beta 1. It's pretty stable. Encourage you to use it. This is some tools we use for monitoring logging. One thing to keep in mind, Prometheus is to scale promises on a cluster in the batch workload, you need to use custom workload, custom customization for the promises to make it work. Fluently works out of box. Provision automation. I want to highlight the injectors. This is key to our multi-tenant environment. Secret injectors, like injectors. Customized is another one. It looks like it's being incorporated in the latest Kubernetes 1.14 upstream the main release branch. It used to be a fork somewhere, and I think Lyft, our internal Kubernetes team, infrastructure team, actually worked on. What customized does is it allows you to have like a Terraform of Terraform, which means it's like you have a composite of construct that can layer across your clusters, which is a very nice way to do mass deployment across many Kubernetes clusters. So remaining work, most of our remaining work will focus on the scheduler part, and most particularly efficiency and parameter composer in tune that. Compute mesh, except one of the goals for us to build a Kubernetes, a Spark Kubernetes is to enable our mesh paradigm. We do have a service mesh running on the Kubernetes side, and we have some data services running on Kubernetes side. With this, we can enable certain data compute mesh use cases, which is an interesting case. Cost distribution, haven't worked on yet. Docker image distribution, Spark 3, and Kubernetes 1.14. This is, yeah, since we're running out of time, you can read this. But basically, Kubernetes can scale, Spark on Kubernetes can scale, but still, there's still tons of work. Community, work across many different communities. Questions?
All right, anybody try to put you in?
Yeah, so really appreciate this part. So my question is, so what is your container churn in the Kubernetes cluster?
Right.
Before you enable reuse of the container?
Right.
And what is the container churn after you enable the reuse of the container?
Right. So container churn, there's two factors. Churn obviously have a container creation time latency and container tear down latency. So we are seeing that when you reach around, for a single cluster, when you have about around 10,000 running pods, when you start adding more, we are seeing container launch latency can upward of tens of minutes before a container can be launched on cluster, which is unacceptable for majority of our workloads. Same thing for termination. So that's one part of churn. Another part of churn is the IP address. On top of that, if you're on AWS, you try to allocate IP address from AWS too fast, too many, AWS will throttle you, so you won't get IP address. What do you do in that case? So our most recent test before we enable pod reuse is about in terms of tens of IPs per second you can allocate. Beyond that, you'll get throttled. Did that answer your question?
Yeah. So, so after you enable the container
right.
Reuse, what's the container allocation rate or container launch rate?
Actually, our launch rate is much lower after we enable this. Also, I didn't show in the slides. We used to, when we start this journey, we are running only a handful of AWS account and a handful of VPC networks. But as you can see, as we scale, even with this reuse, the VPC network cannot hold all those IP addresses. So we are spanning across many different AWS accounts, across many different VPCs through different tunnel network.
Gotcha. So my next question is, try some other options like, for example, running yarn on the cloud to run the Spark job, or?
Yes, we do have a yarn. Like I said, we do have a yarn in the past. We continue to have yarn at present, but one of our goals is we want to consolidate the number of platforms we're going to support in the future. It's a long journey. We haven't completed this one, but we're moving towards that direction. So we still have yarn. We still have a large presence of yarn in our different data product.
Yep. So thank you. I have one more question. Yeah, thank you. So one more question is for the Docker in Docker. So how does the Docker Docker works in production? So do you see any issues?
Yes, obviously, everything failed. But the failure rate is acceptable. So when it fails, we do retries, obviously. The load launch rate is much lower than the pod launch rate. Even in auto scaling at peak time, we only have at most tens of EC2 loads launch per second. So that's comparing to thousands of pods we're launching per second. So that's a different magnitude.
Yeah. So thank you so much.
Yeah.
Any other questions? Raise your hand so I can pass the mic.
So the container reuse, is it available as part of the open source Spark, or you made some changes to it?
The Spark container, majority we are based on, like I said, we have different versions. For 2.4, it's as close as the open source you can get. We brought a few changes, mostly on the resource manager part of the Spark. In Spark, when you launch the cluster controller, that one part, we changed a few parameters. You can look at, I think we checked in some of the changes to our fork. If you go to Lyft on GitHub, there's a Spark fork, and take a look at that.
Oh,
Yeah.
Any other questions? You got it back? Any more questions?